Alright, so now I will teach you on how to draw a label energy profile diagram. Also, after that, I will include the one with catalyst as well. Okay, so let's have a look at the question. Okay, the question asks you to draw an energy profile diagram for the reaction of 2 moles of A plus 1 moles of B produce 1 moles of C. Okay, so we have a potential energy of reactants here, activation energy, and also potential energy for the product. Okay, so the question can be in any form. All right, so sometimes the question also could include the information about the delta H, whether it is positive or negative. But in this question, it didn't give you any information about delta H, but we have the potential energy for reactants and also potential energy for product. So let's start drawing the diagram. Okay, so here at y-axis, we have a potential energy. Right, so here we have the potential energy, which is the units for the potential energy is kilojoule per mole. As for the x-axis, just put it as reaction progress. So we know that we have two types of enthalpy. We have endothermic reaction and also exothermic reaction. So how are we going to know which enthalpy is it for this that is applied for this reaction? Okay. So we have the potential energy of reactants 350 kilojoule per moles, while the product is only 250 kilojoule per moles. So here we can see that enthalpy of reactants is higher than enthalpy of product. So means that our diagram will look like this. This is the reactants at 350 kilojoule per moles, which is we have 2A of gas plus B. Alright, and then we have a product, the enthalpy is much lower. So let's say the 250 kilojoule per moles is around here. So we have C as our product. Alright, so your energy profile diagram should be look like this. Okay. So make sure you label your reactants and product. Alright, and then now label the delta H. Okay, so since the enthalpy of reactants is higher than enthalpy of product, okay, the delta H is always labeled from reactants to product. So since reactants is higher, so it will go downward. So the delta H for this reaction is actually negative value because it goes downward. But if you have delta H positive, means that the reaction is endothermic reaction, the arrow will go upward. Okay, so means that the enthalpy of product is much higher than enthalpy of reactant. It should be look like this. Alright, so where the delta H will become outward. So the delta H value is positive. So this is for the endothermic reaction. So basically this reaction is exothermic reaction. So next we can calculate the delta H value from these two. Okay, because we have this value and this value, actually you can calculate it. So we could answer the B here. If the reaction is exothermic or endothermic, explain your answer. So it is an exothermic reaction because the enthalpy of reactants is higher than enthalpy of product. Alright, so I'll gonna show you the calculation later, but first let's complete our diagram first with the label. Alright, so next you have to label the activated complex. The activated complex is always placed on the top of the diagram here. Okay, so here we have the activated complex, or you can call it as the transition state. Right, so here is the activated complex. Next, the activation energy. All right, so the activation energy is from the reactants to the top of the activated complex. So from here to here. We use this arrow, okay, and then label it as the EA. So since this one is for the forward reaction, so this one is the EA forward, which is 100 kilojoule per mole. And now let's calculate the delta H value for this reaction. So this one is the 350, this one is 250. So just subtract it, 350 minus 250. So we have negative 100 kilojoule per moles. Okay, why do we need to put the negative sign here? All right, because this reaction is an exothermic reaction. The enthalpy of reactants is higher than enthalpy of product. Okay, so means that actually the delta H is the enthalpy of product minus enthalpy of reactant. So 250 minus 350, that's why you got negative 100 kilojoule per mole. So since this diagram is for the forward reaction, if you draw the reverse reaction, okay, it should look like this. Right, which is this is your C, this is A plus B, okay, 2A plus B. So A, the question asks you to calculate the activation energy for the reverse reaction. Okay, we need to calculate for the reverse reaction if the forward reaction is from reactant to the top. Okay, so now if you reverse the reaction, C is going to be your reactant. So the activation energy is from C to the top of it. So basically, it is from C here to the activated complex. Okay, jarak ni. Alright, so the EA reverse is, okay, here from here to here is 100 and then here to here is also 100. So the EA reverse is actually 200 kilojoule per mole. Right, just ignore the sign here. Right, so kita nak tengok jarak, so ignore dia punya sign dekat sini. So, because the sign here just want to show that the reaction is an exothermic reaction. Okay, heat is being released. Let's say you want to show the energy profile diagram if the reaction here you add a catalyst in it. Okay, so the diagram should be like this. Okay, just this diagram you have to draw it as well. Okay, and then you just add this one. Yes, we just add this one to show that the activation energy for the one with catalyst is much lower than the one without catalyst. And then level the activation energy for the reaction with catalyst. So here is the EA with catalyst. Okay, as you can see, the EA with catalyst has much lower value compared to the one without catalyst, because catalyst speed up the reaction by providing an alternative pathway with lower activation energy. And also don't forget to draw these two on the same diagram. Don't separate it into two different diagrams. Okay, you must draw it on the same diagram because you want to show that the EA value here is differ. Okay, the one with catalyst is much lower than without catalyst.